Hear that?
I got kind of frustrated.
It's okay. It's okay. What is this? Quantum?
Yeah.
It's okay.
I mean, because he said he was gonna take it for, you know,
Extra credit?
yeah. He did not.
It's an interesting conversation.
Just take it easy.
Okay, the target today is this fellow, and we're going to do sort of from the ground up, ground state of vibration, and the classical vibrational theory, and then we'll work that into a little bit of the quantum vibrational theory, which is, a little bit like the way quantum field theory is done. You do the classical electromagnetism, and then you quantize oscillators, right? Think you're actually doing quantum mechanics, right? Little do you know. So SF6 is the prototype for UF6. You have to realize that in 1970s, the United States was fearing that its oil sources were going to be inadequate for the number of population, and especially population of vehicles. So they thought that the switching to nuclear reactors, which they already had, but now they wanted more. And the question was, where are they going to get the uranium? And you need uranium-235. And you also, where would you get the plutonium? Because some reactors use that. Well, uranium F6 was the target for the Los Alamos laboratory. Molecular isotope separation, MLIS was the name of the program. Livermore attempted to do it by atomic. That soon proved to be chemically impractical. So the spectra of this became very important. And for someone like me, working at the lab was not cleared at the highest level. It was top secret to look at the UF6. So we did all of our theory with SF6. And we'll describe a little bit of that today. The basic idea that I would like to do is go really into the coordination and labeling of the vectors. We've already done a very simple normal mode problem involving hexagon, triangle, that sort of thing. And in chapter 30 of the quantum theory for the computer age, we do the full analysis of the classical Hamiltonian, called the Watson Hamiltonian for molecules. We'll stop short of that. We won't be doing that in this class, but it might be worth your time to look at that, and I'll refer again to it when we talk about the Coriolis effects that come up down here. So let's go ahead and get started. Here are our pages of references. If you're looking for this particular object right here, International Journal of Molecular Science is one of the references for this thing, and that one works. There's the full reference without a link on it right now. We ought to go ahead and just put a link on that, make it available. That top line there doesn't seem to have links, but these are active, the ones that have underlines. Anyway, then there's our extra stuff. So, we've seen this picture right here. I'm going to try to keep these screens synchronized, of the octahedral symmetry. And that means we're looking both at the O group, which is in this rectangle right here, and the OH group, which is the whole shebang that's there. And remember, the tetrahedral group is isomorphic. The TD group is isomorphic to the octahedral group. If we had another class, we would have started with the tetrahedral modes, but octahedral and a cube, that's two tetrahedrons, so it's not that much of a step to jump up to that which we'll do today. But remember, 5 classes, that means 5 kinds of irreducible representations, and we're going to use all of them, and some of them multiply, in order to analyze the modes of this devilish, sort of devilish octahedral molecule. So This is from that International Journal of Molecular Science article. And remember the cube that lets you have sort of a slide rule, the character table, some correlation tables, and we're going to particularly use that one to get us started here, because we've already done a simple mode problem that just involves the octahedral vibrations where the outer atoms move radially. And we'll talk about that in just a minute here. So this is a connection between the notation that we use on this newer stuff involving the International Journal of Molecular Science. That's a good link right there, just to get into the octahedral part of it. But this comes from the textbook, the old 1993 Principles of Symmetry, Dynamics, and Spectroscopy. And of course, in our very last class, which will be on exam day, we're going to try to look at the icosahedral molecules, but we're going to jump to the big one, which is C60. And 60 is, as I was just joking before the class started, the good news is that C60 is only 10 times as big as SF6 in counting the outer atoms. The bad news is that the factor of 10 appears in the exponent of the analysis for hyperfine structure. So that makes a monster of monsters. But the symmetry is already quite monstrous, 60 elements. You'll see today that we have to struggle a little bit to get the modes of a structure like that. And TC has been working on getting a program working, which may be able to show as we get to the point of calculating those modes. So here I want to look at the, first of all, the Cartesian coordinates that you would use. Now this is straight out of the Wiley textbook, Principles of Symmetry, and it's in chapter 4, and it's kind of an ugly picture. Made with the old-fashioned graphics that you did with funny little pens and a stenograph. And I want to point out, first of all, that the coordinates that we've already done an analysis for are the radial ones, which are indicated by these arrows that come off of the green lines here. For example, if this was your starting point, A, B, and then a rotation of B, those are the sort of the origin of our group orbits. We apply then group elements to label all of the other coordinates on the outside of the molecule, and then we've got 3 more that we've got to worry about at the very center, where the sulfur or uranium atom is sitting. But the fluorines, all 6 of them, have each 3 coordinates. And the radial coordinates, that's something we've already done, and I'll repeat that just to get us, make use of it to do this problem. And there's some weird bonding things here. We're doing a very crude job here of putting springs that go straight between the nuclei. That's not the way nature quite works. And also putting in little circular springs here to indicate covalent bending, restoring forces. So there's a lot that's wrong with this approach, but once you get the group theoretical ideas down, then it's easy to change the Hamiltonian and redo the problem. So just getting through this once is a bit of a challenge. Now, in addition to the radial coordinates indicated by the green arrows and lines, angular coordinates, there's twice as many of those. Okay, so there's 12 angular coordinates, and I haven't pointed out all 12 of them, but anything that's indicating motion perpendicular to the axis, symmetry axis, the 4-fold symmetry axis, is got 2 coordinates labeled by a more or less arbitrary choice of group elements, because there's a lot of subgroups and cosets. Coset labeling really should be used for this, and we haven't done it. This is before we really discovered how to do that. In any case, there is, in addition to the radial and angular coordinates, there are 3 central coordinates. So basically it boils down to the A for the radial, B for the angular, and then C for center. The three coordinates on the center is another vector representation. You know that's going to be described by T1U, irreducible of octahedral OH. So just to do the arithmetic here, we have 6 radial dimensions, 12 angular dimensions called the B dimensions, and then finally the central gives us another 3, so that's 15 plus 6 is 21 total dimension, total degrees of freedom for this molecule. Well, nature makes this a little easier because we're going to be able to subtract 3 translations that go with the T1U thing, and that takes a little bit of effort, and we're not doing it in the most elegant way, but we'll do it elegantly enough to get through it. And then a T1G doesn't show up too well here in this particular projection. That's another 3. That would correspond to the rotations, which we do by Euler angles and do much more elegantly. So they're out as well. So we really end here with 15 what are called genuine vibrational modes. Okay, so that taking that 6 out reduces the problem, but taking it out is a problem that we have to solve. So the symmetry, coordination, and mode labeling of this really is what we have to do carefully. Okay, so just to remind you, and this goes back to figure 4.3 in the Principles of Symmetry dynamic spectroscopy thing, and also we've got this worked out on our own, this class is lecture 16 on page 15. That's an active link. I'll actually use one of those just to go back and look at it real quickly. But if you recall, we made a big fuss about the radial vibrator model. So here are the A part of the SF6, where only motion in the along the fourfold axis is allowed. And the result was to have a nice analogy between what we really wanted at the time when we were doing this stuff, the wave functions of the angular momentum in the frame of the SF6 molecule, which is a very pretty sort of thing. So as I said, I should be keeping this one up to date here. Let's go ahead and look just quickly at a beautiful picture of the modes that we had to do then. Let's see if that shows up here. Takes a little bit of time to come up. But there's a beautiful picture, okay, of the E1G, the T1U, and the A1G singlet. So you have a singlet, a triplet, and then an E1G, and then there's that ratio of 2 to 1 splitting between E and T1. Doubled is the splitting between T1 and A1G at the bottom there. Okay, and I'm going to see if I can make the view here a little bit better by entering a full screen. Bring it up a little bit. It didn't help much, did it? But anyway, this is something you click on just to refresh your memory about the quantum analog for this classical problem that we're interested in today. And we'll see that the actual molecule has something like this ordering here, E, T1, A1, in a certain situation, which we'll talk about later. But in any case, when we did this, we looked at the subgroup correlation, this A1 induced to the octahedral OH. In other words, we looked up on the scalar column, the C4V symmetric axis, then giving us the induced representation that involves all 6 axes. And that gave us A1G, EG, and T1U, which are the modes that are shown in these drawings here, this crude old drawing here and that monstrosity over there.
And this is what we're interested in right here. When we say plus and minus phase, well, in a classical problem, that means your vector is pointing backwards. When it has a minus sign, it's pointing outward when it has a positive sign. So the plus and minus signs are indicated very loudly on that color diagram over here. Here you don't need them because the arrow points out whether you're going in or out. So that basically the modes are two atoms going along the x-axis, two atoms along the y-axis, and two atoms along the z-axis for modes 1, 2, and 3. Remember, the z-axis is horizontal for this sort of pictures that we've been making. And then, of course, there's the breathing mode, where everything just goes like that. That's a name that spectroscopists refer to. Usually it's the grounds, the lowest vibrational modes. Very often, well, I should say sometimes the lowest modes are the breathing. If it's got lots of stretch springiness, then the breathing mode is very often the highest frequency. With SF6, it's pretty near the top. So we'll be doing that. Now, what we need to get off of the A radial vibrational modes and get the rest of this problem going here is to look at the transfers, that is, do an induction involving the E two-dimensional representation of the two vectors that are perpendicular to the z-axis. That is, the two coordinates that we've left off of this description. So we can tell right away what those are. Just look in the E column here, and you've got essentially the rest of the modes that you're going to see for the SF6. And I'm going to go ahead and shut this one down here and go back to the lectures there. And you can see the next thing coming up here. That's this column right here that has the induced representation by this subgroup C4. We picked the z-axis, and then it's asking, well, what if it tunnels to all of the other equivalent sites? If we're talking quantum mechanics, but here we're talking classical, still works to think that way. So I'm going to be seeing here a T1G, a T2G, then a T1U, another one of those. We've already, looks like we've got one of those in the radial department, so here's another one. And then a T2U, the very last row here is indicating we've got one of those as well. So that's takes care of the A and the B. The only thing missing now for this discussion is the central, the uranium or the sulfur that sits at the center of SF6 and has three of its coordinates, and that's a T1U, another. So now we got three of those T1Us, okay? So group theory is not completely labeling these three. It says they're all T1U. So we've got some sorting to do, and that's the major problem with this molecule that we have not mentioned much in this class. It's the dirty part of group theory. So we'll have to handle that. That's the key thing here. We need to do some mode labeling here, and in order to get the projection operators working for us. So here's how it goes. As I said, we've got three radial modes, a singlet, a triplet, and a doublet. That's the one that had that beautiful bunch of pictures for our tunneling model. But this is just vibrations we're talking about here. So the radial vibrations are here. And A1G is ready to go. We already know what that looks like. So that's going to be one of our modes. And I don't see any other A1Gs in here. So no diagonalization or sorting or anything needed for that one. That one's done, ready to go, ready to vibrate. And at a pretty high frequency, it will do that. The next stop on this thing right here is EG. those two are ready to go as well. And this is just a sketch of what we have still on the screen there. The two E's at the very top of this diagram here, they're ready to go. They're going to be modes because there are no more EGs in there. So this is orthogonal through the Hamiltonian, or whatever you want to call the dynamics of this thing. And we're going to have a force matrix, actually. The EG is inviolable and will perform as best it would over in that simple problem there. And I see a T1U, okay, and that's the rub, okay. Now there is a T1U that's shown in this sketch of all the modes, okay, but that sketch needs some work. And in particular, this T1U needs to be mixed in some amount with all of the others. There are two others. Okay, so we've got a 3 by 3, it looks like, matrix that we might have to diagonalize if this molecule was actually to include the translational degrees of freedom as part of the problem. And remember, when we did our vibrational analysis before, we always had springs holding the thing that we call the molecule. And that's a good thing because you could imagine that if you really were doing sensitive spectroscopy in a trap of some kind, or the molecule is in a lattice in some way, or sitting inside buckyball in some way, you see, then the translational degrees of freedom would come alive, quantum mechanically speaking. And that'd be a beautiful experiment. And we hope that we see some more of that as we get better at doing spectroscopy with trapped molecules. So right now I'm saying I got to get rid of one of those T1Us for this problem, but come the time, we won't discard that in some future experiment. So we have mixing with two other T1Us, and translation must be discarded. Okay, so those dashed lines we'll talk about in a minute, belonging to the angular side and then to the central. We've got to deal with that. That's the dirty part of this particular symmetry analysis right there. Okay, now let's look at the angular, the B-type guys, the ones that are perpendicular to that. Not shown in that thing, but mentioned at the bottom. So we've got these guys right here. And then, of course, there's the central fellow that's not mentioned in that slide. Okay. So let's bring that set of slides up to where we are right now. Okay. So there are 3 T1G rotations in this problem, and we're going to discard them. That's because we already have a really elegant theory for the rotation of the molecule, and that's all that is. And it's a lousy description of it because this one is telling me that to rotate this molecule, I got to follow this line here, you see. And this one has to follow that line, and this one has to follow that line. Well, that's complete BS. You know that because that line could extend away out here, and this one could extend away down here, and all you'd have is a great big molecule slightly rotated if you followed that normal mode, right? So we're happy to see this one go. We have other ways to do rotations, and that's what all this Euler angle stuff was all about anyway, and we've got wave functions for that. So that's one that we probably will almost always discard, but I can envision a trap that might also trap the rotation, right? It might make it into libration. So maybe someday we don't have to, we don't discard that as well in an experiment. Okay, but for us, we're out in the open, we've got to discard it. All right, now what about the rest of this? We're about halfway through this manifold. T2G is ready to go. It's a funny kind of shearing. That's what it does it. And then it does it to another side, and then to another side. So this one, just this is a beautiful mode. Okay, and we're ready to accept it as part of our deal here. Now, what about T2U? That's kind of a weird one, and it's odd. This one is even. in inversion symmetry. This one is odd. This is where two atoms go like this. That's got a U on, Ungarada, okay? But it's ready to go. That's what we like, is something ready to go, okay? So we're all set here, except for, we haven't mentioned the central ones, okay? That's the very bottom one there. One more T1U to go with this one. So we're going to have this one playing footsie with this one, and the translation, we got to get it out of here. And that's not easy. You can't just throw it away. We've got to manipulate a combination of what we've made by projection to get that out of here. Okay? So this is a sketch of what we've got and what we've got to do. Any questions about that? Is that pretty clear? I'm not asking you to be clear about all of the ways that we can do this elegantly. I don't think I know the answer to that. But I've got some answers, and that's what we'll discuss today. Okay, so in order to do the projection, we're going to have to use the irreducible representations of the octahedral group. And they're sitting waiting on a page we've already looked at, and we derived some of the things. Here is the complete table. If you look in PSDS, it's in black and white, and not easily, it's all on different pages. But back in class 17, lecture 17 on page 85, just click on that, and you'll come to this particular thing, and then the derivation of it precedes that page. So then there's a character table to take care of the A1 and the A2. Now remember, this is not OH, this is only O. But all you have to do is do plus or minuses on each of these matrices in an orderly way, and you'll get the U and the G's that go with OH. And remember, we classified these things by polynomials, binomial in this case, and just a monomial, an X, Y, and Z was what the vector was. So all of that is now in Technicolor instead of black and white that you have there. So this references the one you would want to look at if you want to follow up on this. And we are going to use those numbers. And we're going to use them in a efficient way. That is, we're going to use them coset by coset. They're going to be, they are displayed in cosine-factored ways so that the projectors can just write down about 4 numbers and they're done. Okay, now here's the rough part right here. We got to do something with these modes. Now, right here, I've just gone and listed all of the degrees of freedom. That is, here are the A-type coordinates that do with the radial motions, like R1 cubed, which is right here. Okay, R2, it's right here, and over in the back side there's R2 cubed, which is right here, and then there's an R1 associated with one of these guys, there he is down there, and so forth, and then of course there's the unit one, just plain old A sticking out on this side. So there's the A subspace. And then the B subspace, all 12 of them are sitting there. Those are the angular ones. And finally, the last 3 of what's going to be our force matrix is the 3 C's that have the uranium or sulfur atom in mind. Okay? So, let's take a look at the A space. First of all, what's something that translates? That's the good old T1UA. Might be capital A associated with the A space. It's not a good mnemonic. This is not the angular. The angular is the B, but A stands for radial in this case. This is one of the coordinates, a translation, and it has a momentum. There's a normalized vector, 1 over the square root of 2, so the momentum that we're talking about here is 2 over the square root of 2. So it's the mass of the sulfur, mass of the fluorines. The fluorines are moving here, everything else is standing still. It's only 2 of them going back and forth. That's the A-type T1U, okay, which you see listed here and here with those numbers, okay? So that's the group labeling of this particular motion. Obviously that is probably not going to be a mode for us. That's going to mix with the other T1s, particularly if you are asking, does this thing not have any translation momentum? And then here's another one. This one has momentum of 2. It's 4 times a half. It's one of the B guys right here, okay? And you see where I put those 1/2s and -1/2s. The -1/2 obviously needed right here. And then this one right here, let's see if that's in the direction, so it's plus, you say. But this one is counter, so you get a minus for it. Okay, and all the others are positive. All right? So there's a thing that's not a mode for us because it's got linear momentum. We only want modes that have none of that linear momentum. Okay, and then finally, the guy in the very center, you put him on the number 1 coordinate or any of the others that he has. Well, he's clearly got momentum. It's the big mass now times, and that's just a unit vector there. Okay, so we've got to do something about those 3. We've got to basically combine them into 2 states that have 0 momentum and throw away the third one, which has all the momentum. So we've got to somehow shovel the momentum that each of them have into a single mode. And here's the first try at that. I'll just take the radials and go this way with just the right amount, that is with a factor of √2, to counter the momentum due to this one, which is now going into the board. Okay, so there is a mode, at least a trial mode, that has no momentum. That's one. We're going to need all 3 of them in this act right here. And so here is a mixture of all 3 spaces and in just one direction. And now we got 6 times the mass as the coordinate of the central atom, and then 1 times the mass of the central atom for each of the exterior fluorine atoms. So the mass of fluorine is little m, the mass of the uranium or sulfur is the big M. Okay, so we've got 3 vectors here, we'll call them T1U and T1U prime. And they're the ones we're going to use. Now, who are we going to throw away? We're going to throw away a rigid translation mode, okay, where they're all going with the same amplitude in a particular axial direction, which we've picked to be the thing sort of out of the screen here. Okay, so this is what we're getting rid of. We're getting rid of that because it is not a genuine mode. That is, it doesn't have a frequency other than 0. Let you look at those for a little bit here before we go on. I'm going to move the slides over to that point. Okay, so by summing those appropriately, I make a mode that has all momentum, and then the other 2 have exactly 0 momentum there. So that's our candidates for getting the actual modes of this molecule. And they're not orthogonal or orthonormal or anything. So we're not able to go ahead and just use Hermitian operators. We're going to need a force, a mass, and an acceleration matrix. We're kind of going to just write things like Newton's law, F equal ma plus or minus ma. Okay? So the acceleration matrix, and it'll be a 2x2 matrix for the 2 T1Us that we've got left that have no linear momentum in our ABC mode dynamics. It involves all 3 of the A, B, and C spaces. So that's the thing we've got to deal with here. Now, here, and this is something that I'm not going to point out step by step here, but all of the springs that we've got going on the Hamiltonian for this thing, the J, K, and then a thing called B for bending. Remember, I pointed some of these out on the original diagram, coordinate diagram for this thing. So, as I say, quite a few modes. A1G for 1, EG for 2, so that's 3 modes accounted for there. This one's degenerate, so that's a doublet inside that degeneracy, but this is just a single level, frequency level, frequency squared level. Remember that we're doing classical physics here. We're doing a Newton-like mode equation. Let me put it on this screen as well here. We're doing a Newton-like mode equation with a minus sign. Mass times acceleration is equal to minus, and this is what we called the K matrix before. Okay, I'm just putting force on it for the make you feel comfortable, I guess. Back to high sophomore physics, F equal ma, except we got a minus sign now, right? It's mathematicians' force. Okay. Anyway, the eigenvalues of the matrix equation are going to be squares. So F times m inverse is the acceleration matrix, and its eigenvalues are frequencies. So that's kind of cheesy, I have to admit. But, you know, beggars can't be choosers. So we've got already here T2U and T2G. We've already got, just with a little projection summing over the coset liters, we've got 2 frequencies here, one K plus B over M, and the other 2 times K plus B over M. And this one is K plus J over M. So those are the springs that we put into this system, and we're going to live with them, live or die. Now here's the hardest part. I'm going to take the zero momentum basis, which consists of that thing, it doesn't have any mention of the masses of the atoms, big M for uranium and little m for the fluorine, but this guy right here, the second of our 2 zero momentum states, has got 3 terms. So we got to make a matrix out of these 2 T1U's, starting with just a matrix product involving that thing. So there it is, this thing dot itself with, we're going to try get the matrix for Q equal force matrix and Q equal mass matrix. So that's the order of the day for getting us the solutions to this problem. The eigen solutions to this problem. Not trivial at all. Okay? So at first we discuss, we're going to have a Q AA, okay, that's this guy right here. We're going to have a AB and a BA, okay, that's this guy and this guy, and then a BB guy, that's this guy right here that come out of this product. And this is just the first matrix element of a 2x2 matrix, okay? And each term is going to be projected. So here's where you use the projection using T1U irreducible representations. And that's not the hard part because there's only a few numbers that go into that. So here's the result. This is the force collection here, and we would like to make that into a single matrix that involves the force. And so that's the matrix there for the force. And then there's a mass matrix that's kind of weird that has 3m, 3 times the outside fluorines. Here's the 1,2 matrix elements done sort of the same way. I'm skipping some steps here. Fortunately, this one doesn't have an off-diagonal component. But of course, the force does have an off-diagonal component, and that's the thing that's going to really determine the shape of our modes, that number right there. And then finally, there's the second diagonal coefficients that for the force gets you that, and for the mass gets you that. Okay, so that's the deal. And we've got to do the inverse of the mass matrix times the force. And then this way we avoid the nastiness that's associated with having non-orthonormal collections of states. I think we balance them very specially to make sure that the momentum, linear momentum, was out of here. But in the process of doing that, we have to, have an M matrix in addition to the force matrix. So you get a pretty complicated little 2x2 matrix to take care of the pair of T1U's that can still be genuine modes. And it's not an elegant solution by any means, but you can talk about the sum of the eigenvalues and the product of the eigenvalues just from looking at the second equation of this crazy thing here. So we've got a sum S, and we got a product P of eigenvalues in terms of the spring constants, okay? And that's useful for some things just in itself. But we really need the frequencies, right? And it's frequency squared of the eigenvalue, so you have a big radical over what would normally just be an eigenvalue for a quantum problem, right? Now that begins to ask another question is, when you quantize this sucker, what do you get? And you get a lot of things, and that's something I'd like to kind of look at here. But first, let's just take another look at the, first of all, now the actual formulas, and these two right here are being written from that formula I just showed you. See a minus sign now, which I never noticed before, missing from there, but this one has it in the right place, and this is a plus and that's a minus, so this one is the high guy and this is the low guy. There are your two T1U's. And let's see what else I had to do here. This I forgot to fix as well. This is a typo in the textbook. These are both T2U's. This one should be a T2U as well. So this was a ready to go mode, and so was this, and so was that. And let's see if I've got that. And this one too. This is ready to go. That's a thing that just has these spring constants directly in the radical. Okay, so that's those are our prisoners for this episode of the SF6 analysis. Okay. Now let's take a look at how these things vary. See, this is what's fun about having a formula for these things, is you can say, oh, what if I let the bending change? Or more likely, what if I let the ratio between K and J change? Those are the two spring constants that we had, sort of nearest neighbor and next nearest neighbor. There was a J that went all the way through the molecule. And what we're doing is we're varying that compared to the spring constant K that connects the nearest neighbors. And you can see that this is considerable variation. But which one fits the actual data? Okay, you can see that the T1U, A1G kind of are serving as fitting parameters here, and then the rest of them just fall where they may, but they're not too far off, except for this one. This T1U is looking like it's a lot higher than the T1U that comes with it. Now, this is the standard spectroscopic naming nomenclature for the modes of this molecule and UF6 as well. All of the hexafluorides and hexachlorides and the hexabromides. There's just a whole bunch of molecules that make octahedrons, mostly halogens, but that doesn't cover it completely by any means. So this naming becomes, you memorize who nu 1 is and who nu 2 is. That's pretty easy. This is a singlet and this is a doublet. So nu 1 and nu 2, that makes sense, right? The E is a doublet, right? There's the E, but if you bring then one finger in and you've got a doublet, right? So that's the way I remember the E, but it is nu 2, so that's good. And then this is a three-dimensional one, nu 3, the next one in line here, okay? And they call the highest one nu 3, but then the other T1U is called nu 4. That's kind of weird, right?
Well, these guys aren't artists, right? They got to get the job done. So that's what we're stuck with. That's the naming that we're stuck with. Okay. So here's where they rearrange as we get to the place where SF6 is living. All right. Now here are the ones that they were paying money for, big money for this. Okay. So here's new 1, new 3, and new 2. Here's an A1G, T1UE, not too different from what we get from the radial motions, right? Except that instead of the T1U being real close to the E, it's more close to the A1. Aside from that, it's in the ballpark of the problem that we have. But look at plutonium, T1U and A1G get real cozy in the experimental data for plutonium hexafluoride. The Neptunium hexafluoride sort of in the middle there. There are a whole bunch of others which I haven't been able to find data on. These are really the only candidates for possibilities for interesting isotope separation. Now, what's disappointing about this model is that the other 3 kind of come out in maybe the right order, sort of, but they kind of hang behind for UF6. Okay, and since that's the one that was paying the bills, it's kind of embarrassing not to get a model that can fit these better than that. So you can see this model was a first try. And then the real serious work, which involved huge computer calculations, did a lot better than that on fitting the experiment, obviously. So big money was on getting this right. Now, when it comes down to it, though, pretty much they aren't interested in these. Now, there's a T1U down here. It's dipole active, but the one they're interested in is this one here, new 3. It's a 10 microns. 10 microns is CO2. Okay, so you get the picture. If you're going to separate the isotopes, you got to use the fine structure of T1U up there. So just to give you an idea who's paying the bill around this project. Okay. Now this is going on in France too. France really wanted to have uranium, so the Bordays were given a much more esoteric sort of project, and they took advantage of it, and we'll be talking more about that later on. So here's a comparison between those heavy atoms and the simple SF6, which is in every transformer box that you see along the highway for medium voltage house current type application. And just this week I've heard 2 of them blow up. We sit up on the hill here where all the power grids meet for Fayetteville, and so there's a whole bunch of SF6 boxes. And I was sitting here working my computer, and all of a sudden the battery holder, the thing that fixes it so when the power goes off, the computer keeps running. I don't know what's the name of it.
UPS.
Yeah, the power supply. I heard it click, you know, and of course that meant the computer was now running on the battery. A little beep, and then I heard bang. I mean, at first the click, and so the lights also went a little down, and then about a half mile away, because it took about 2 seconds for the bang to show up in my ears. Okay. And then another one heard in the middle of the night. Just well, it was last night. So we've been losing SF6 like crazy up on top of the hill here. You need some flying there somewhere. Okay. Anyway, let's go on here. This is what Los Alamos provided me. This is Robin McDowell and Jay Ackerholt worked really hard to study. Well, here's new one. That's the A1G ladder. It's very harmonic. Here's new 2, the E ladder. Okay, harmonics.
okay? Here's the one they're really interested in, nu 3. It's right around 10 microns, which is 1,000 inverse centimeters, 1,000 waves per centimeter. Okay, that's right in the middle of the infrared. Okay, and then double that, still accessible, so they had data on that one too. And the whole idea was to dissociate the thing up the 2 nu 3, 3 nu 3 ladder. That was the deal, and it worked. They actually did. This was discovered by the Russians accidentally. They simply left an infrared laser on overnight. They went home forgetting to turn off the CO2 laser and a bunch of SF6, right? Next day, they come in and the chamber's all yellow. The sulfur was all coating the inside of the laser. They had dissociated sulfur hexafluoride up the ladder. That was magic. Nobody thought that was possible. So that's what really started the project. When they discovered that, now people did a repeated experiment. Then as you get over into the combination tones, wow, the spectrum. So you can see if you heat SF6 up and start getting these things going, you got a real mess. The spectroscopy just, you won't be able to see through it. And that's the problem with buckyball. That happens at room temperature. Room temperature, you're in something like this with buckyball. Okay, until you get down to about 150 Kelvin, you can't see through that spectrum. It's just a mess. Okay, so there's little things to notice about all of this. Okay, now here's something that's really pretty. And that are the 2 nu 3 modes. This one at 10 microns, 1,000 wave numbers, or actually 947 if you're right at the center of the Q line. So that's what we want to talk about, is a little bit of the quantum mechanics that's associated with the angular momentum that this clearly has. Here we see here a really big right-handed rotation of the heavy part of the molecule. And then some very weak, and I mean the area of the ellipse is pretty small, left-handed motion. And all I'm doing is taking this mode that we just got through calculating the eigenvalues for, that means we have the eigenvectors too, just take that one and add it 90 degrees out of phase with the same thing going in the y direction. Okay, so it's basically EX plus I, EY, called E plus. And the idea of making that, now these guys right here I call standing wave modes, but we put two of those together in a 90-degree arrangement, which is what the molecule is going to do if it starts to rotate, because it's going to think it's got a magnetic field, something that's proportional to velocity. It's actually omega cross V, but you know, that's a little more idea that you can't tell the difference between having a charge in a magnetic field or just having that particular mass sitting on a rotating structure. It will start to orbit, cyclotron-like, if it's being held by springs. Now this one over here, you'll see that a lot of motion here, that this one right here was right-handed. What this one is doing is favoring left-handed motion more. You see it there, you see it there, and there, and there. And the ellipses are quite big, so what we end up with is more left-handed than right-handed on this one. Now that determines the Coriolis effect for these two. This is the one that is at 16 microns, 600 or something inverse centimeters. This one at 1,000 or 10 microns is a right-winger, and this is a left one. So this is a liberal molecule, and this is a conservative molecule over here. Okay, now the 10 micron one, of course, is the one they were interested in. But we'll look at both of them. Let's look at the spectra, and I want to show you a graphical way to handle a lot of this spectra, not just this Coriolis spectrum, which is what we look at when you do spectroscopy at low resolution, you can see these effects very clearly, most clearly for the 16 micron one. So nu 4 is what we're going to be pretty much talking about the rest of this class today. But I want to show you a row vibronic nomogram that I put in one of my earliest papers, and it's only now being used because now they're doing two-dimensional spectroscopy, but the nomogram was good for any dimensional spectroscopy, as you'll see. And let's have a gander at that in just a minute here. Now, I'm getting behind on the other screen. I'd like to keep these things together. So I'm going to bring this one up to speed. There's the overtones. There's that. That's the thing that we're going to be fighting with, the two possibilities. What are the differences between nu 3 and nu 4, okay, as far as Coriolis behavior, okay? So, and while we're at it, let's remind ourselves of what term in the Hamiltonian, now this is a quantum mechanical, supposedly Hamiltonian, that we are claiming that we have some control of, when in fact, by getting the vibrational frequency, we had to use classical ideas through and through. Once we get the classical things, then we just say, oh, well, let that oscillator be quantum mechanical. Okay, so you got to utter some Latin phrases, you know, and you've got quantum mechanical oscillator, right? Well, we know our rotations are quantum mechanical, and we've been looking at a little bit of that already in this class. And we haven't really, until now, had a nice way to look at the Coriolis effects associated with classical or quantum oscillators, and then the Coriolis effects and centrifugal effects associated with the quantum mechanics of this molecule. And then finally, this little guy right here, the nuclear spin, we're going to be talking about that in the next lecture. But there's lots of fine structure here that we can deal with that involve, well, first this is just the coarse structure, and then there's the fine structure that we've been looking at with those level clusters and things. So all that's coming together now in today's expose of SF6. And it's mostly nu 4. That's nu 4. Nu 4 is quite pretty because you can actually see the space at a very low resolution, low by standards now. When it first came out, Fourier transform spectroscopy was like magic. Before that, all you saw was a lumpity lump and nothing more. And now you're getting to see levels with quanta up to 80 or 90 on this side and up to 100 on this side. And this is called the P branch. I've already mentioned that on the first day of the lectures. And the R branch for CO2, I was just giving a crude model then, and then the Q in the middle. Well, let's look at how those are made. Why are they so evenly spaced? Aren't we talking about quadratically variant levels here in some cases with angular momentum? And the answer is yes, but no. This structure here is due to the scalar interaction of the vibrational angular momentum, the thing that makes those orbits have angular momentum now, and the total momentum of this configuration of nuclei that includes the nuclei as a rotor that doesn't have the orbits yet. But when it gets the orbits, then you get what I call Rock's trick here. The scalar Coriolis interaction between the total angular momentum and the L of the vibrations, taking them one at a time, one mode at a time. Okay, so there's a coefficient here called B zeta, and you'll hear if you go to a molecular conference, you would hear B zeta the most. They just say, oh, and the B zeta was this, and the B zeta was that. Okay, it's kind of like a general relativity conference that Feynman used to complain about. He said to his wife, "Remind me never to go to a general relativity conference. All they do is go around and say G mu nu, G mu nu." The metrics, right? G mu nu. And that's the way he found where the conference was when he first went. He was in a text, I don't know where this conference is. And they said, well, it's for gravitation and general relativity. And the guy said, I don't know, I can't help you. And he says, it's a bunch of people that say G mu nu. Oh yeah, it's over on 6th Avenue, let's go. So, it's funny how language helps you. You're up on things like Feynman was. In any case, if you just go ahead and say that this product here is J squared, and then minus J minus L, I mean, this binomial here has got J dot L in it, right? And then you just have to add or subtract these guys right here to make that. Then each one of these things, this is J minus L, which is the nuclear momentum without the vibration squared. This is the total squared, and this is the L squared. So you just put down the quantum numbers for those three angular momentum, and you got a formula for where the Coriolis levels are going to be. That's pretty tricky. I mean, we could have done this a little bit as we went into the spin orbit calculation, but we were so busy worried about, getting the determinants and all that sort of thing. I didn't point that out. But there is a quick way to get some of the answers like that. This is one really good one. So the angular momentum of these vibration orbits and the angular momentum of, they use different letters. N, if you think, but most of the time they have R for rotor. So that's the most common thing. So L plus R, that's the whole molecule. And then these are the parts, the rotor part and then the vibrational part that we're seeing. And it's noticeable splitting, particularly even for a small Coriolis coefficient like this negative one right here that occurs for the 16 micron vibration. Okay, so as I said, this was mostly a liberal. This was a mostly left-handed motion. So it gets a minus sign on that. And a minus sign in that formula lowers the higher ends. So you see the higher ends are on the low side of the splittings that this formula predicts. That's the case if you're a liberal. You don't like getting the big momentum. You want to keep them down, and the people that have less money, you want them to thrive, right? Okay? So that's the way it goes for the 16 micron vibration. Okay? But for the other one, okay, the positive d zeta, and that's what you've got at 10 microns instead of 16. When you go to a higher frequency, shorter wavelength, you discover a very large positive d zeta. So this one is a lot more splitting, and you're seeing the high end angular momentum come up in that case. Positive d zeta makes the higher angular momentum higher instead of lower. Okay, so there are the two modes that we worked out today, drawn in there as best I can given what we have here. And there is what we're going to expect for the levels. But still, that doesn't give me a picture of the spectra. The way people would do the spectra now would be to draw a picture of the ground state levels and then draw lines for each of the transitions that were allowed or that they were interested in. And still, you'd have to go and measure all those lines to see what the spectrum was going to be. And it just blew my mind that nobody had figured out a way to display that. That's called, what is the name of that? Floquet diagram or something. There's a name for drawing lines between levels. That I skipped my, I've repressed it because it's so stupid compared to what you should be doing. And what you should be doing is this. Here are your initial states that have the rotor and the J the same. Okay, so no vibration messing this one up. Okay, so what I'm talking about here is n equal j equals 0, n equal j equal 1, n equal j equal 2. No vibrational angular momentum. That's the ground state. Okay, but when you start the vibration going, very often it has angular momentum with a non-zero b zeta. Okay, So, for example, in 16 micron nu 4 spectrum, that's the one I'll do the nomogram for because that's what we're going to look at now. I will simply go up here and I will just draw lines across here that intersect each one of the lines down here. And we're talking dipole transitions, so at each value of n, I can either maintain the status quo, that's the Q branch, or I can raise it, okay? What I'm talking here is n equal 1, okay? And j equal 1, and here I'm going to raise it to 2. J is going to be raising to 2 from 1. So that's the actual designation, and it shows what a raising gives it to you. It gives a spectrum, it'll be over here. So I draw lines at 45 degrees, I'm automatically taking the difference between a level down here and a particular level up here, and then showing it as an output. Okay? So let's bring this up to speed because I'd like to show a couple of these at once. This one in particular. Okay? Now this one right here that is being looked at, this one over here, is based on the B zeta 4. But B zeta 3, the spectra for it, let me see if I'm in the right place here. This is the nu 4 levels, these are the nu 3 levels right here. And if I projected those across, I get a very different spectrum than what I've got. The same shape, same idea. And the main thing to notice is that the spectrum, you have to turn your head on the side to see it, that's the Q branch there, where all of those things that maintain the status quo pretty much line up on top of each other. And this happens all the way to j equal 88, as you saw in the example that we showed just recently, we will show again. But here, right here is something, P for plunge. What's happening here is that the j value went from 1 to 0. And this is a j value that went from 2 to 1. It's plunging, whereas these are raising values, R values. And they aren't the only thing that can happen. Other more complicated molecules will be giving structure, very weak structure, at intermediate values. They're indicated by the dots here. That's not something we see with these very pristine and highly symmetric molecules. But then it's when you really like to have a nomogram that lets you relate the ground levels to the excited levels. So just to give you that as a tool that you can use on any kind of spectrum that involves transitions that are resolvable. Okay, any questions about this? This is kind of getting to the end of what we need to do today, and that is set the stage for the high resolution stuff that comes out of each of these. Okay, that's the fine structure. Okay, if you're going to use an atomic analog, this is the fine structure, but it's the fine structure associated with something that we don't have in atoms at all. And then there's the superfine structure, and then there's the super hyperfine structure. All those are names that came out of this lab. Okay. So let's just go ahead and look here. Now here are two places you could link up where this giant diagram resides, and we've seen this already. Okay, so we've got a PQ and R structure due to the Coriolis scalar interaction right here. There's the P's, and they're the ones that have the first example that was really clear of the fine structure, hiding inside the 88th bump. This is 80 right here. So you go 1, 2, 3, 4, 5, 6, 7, 8, and you got all this stuff hiding in a single bump. Isn't that amazing? I mean, I think it's amazing, and I'm really thankful. This was my employment for quite a few years to figure this stuff out. Okay? So these guys right here, and what we're going to be talking about next lecture is what happens to various group theoretical things when this incredible crushing of levels that normally don't live with each other happens. So what we're talking about are the AT1E cluster being smashed together with only kilohertz or hertz or close to microhertz or actually picohertz right here. This corresponds to a tunneling time on that weird rotational energy surface that goes for quite a few years. So it's like 100 years or so. Okay, it's like radioactive time constants, right? So this is what we're really excited about and happy about. And this is what we've already looked at. These are the levels that come off of these rotational energy surfaces, and this is the 88th one. And you've got to think of all of these surfaces hiding on top of each other, but this structure shows up in both the level structure and the spectra that results from that level structure. I'll jump ahead on this screen right here to show that. That's some other geometry to get the actual fine structure, but there's a nomogram right there. Okay, so on this time I've got the ground state here, because if I turn it this way, it's so much broader here than it is here. But the form of this is the same as the form of this, and those little quantum numbers, the little n values, are conserved in this transition almost perfectly. Not quite perfect, but almost. Enough so that you don't see much activity between these things. And if you look at it with a magnifying glass, as we will in the next lecture, here's a typical spectrum. That was an amazing find, that particular one. That's Bourdais, one of Bourdais' T1E, T2 spectrum. We have to figure out what's really going on there. There's amazing stuff going on there. But there's amazing stuff going on here too, and I consider just scalar Coriolis effects amazing. So maybe I'm weird, but I think that there's a lot that you can have fun with on this. Okay? What follows is the spin symmetry. So that's what we've got to talk about. So it's what this thing really has in it. This is from this paper right here. That's the link you can click on for this. So that's what's making really amazing things happen in that particular thing. It's called crossover resonance, and this one, there's more than just T1U in this thing. We'll prove that. And EU doesn't have an EG for some reason, and we'll prove that too. And then T2G doesn't have a T2U to go with it, so it doesn't get a crossover resonance with this one, because this is odd and this one's even. Nothing going on between them. So there's all kinds of really neat physics waiting at the very finest levels that are at the bottom of this diagram that we need to talk about. And that will be, now that would be, I would hope, an incentive to see how this panoply of spin and orbit and Coriolis levels, what do they make in a molecule that's 10 times bigger? Where 10 shows up in the exponent as far as the hyperfinest go. We're talking about a spin and a half to the 10th power, 2 to the 10th power. That's how many hyperfine lines. This one's only 2 to the 6th, that's 64. There's only 64 hyperfine states all together. I can almost count them if I was an alien that had 64 fingers. Right? I could count them on my fingertips.
2 to the 60th?
And this guy right here was 60, 2 to the 60th. You're talking a very strange alien who has an octillion number of fingers. Okay, that's a lot of fingers. And that's what this molecule has. Now the other extreme is carbon-12, and it's a godsend because it's so simple. It only has one symmetry species. So the spectrum is very bare at this level. There'll be only the A1Gs to be, well here an A1G only occurs very frequently, so you know AEH you'd maybe get 3 lines. Maybe 4, I forget which, right?
So fewer lines, could you say that it's most likely less reactive? Can you say that? Because then you...
Well, when you think of each of the symmetry species as a different chemical, right? And with SF6, we've got 10 different chemicals. If you were just talking about, you know, A1G, A1U, EG, EU, right? T1G, T1U. Each one of those has this thing that Hertzberg called inviolable, the rovibronic species. And that, you know, for a long time, as we'll describe in the next lecture, that was thought to be inviolable. That is, you would put a bottle of T1Us, and then there was a bottle where you somehow separated out the T1Gs, right? You put them together, and they don't change. Now, how do you separate them? They're so different in properties that it would be difficult to separate them, but it's in principle possible because they don't change. It's just like orthopara hydrogen, right? The ortho hydrogen with its spin 1. It just goes around and keeps its spin 1 until it hits an iron wall, right? And then it blows up a blimp hangar in World War I, right? But most of the time it doesn't do that. And if they kept it in aluminum or something that wasn't magnetic, that ortho would go around and keep its spin 1, be ortho all the time. And the para, it has no spin, it would go around with this anti-symmetric combination of spins and symmetric spatial combination. It would just keep that. Well, these molecules do that too. Until they cluster. Until they get out here in the ends where these species are brought right on top of each other, where they can resonate. So that's what we're going to talk about next time, is what that involves. But of course I'll mention once again how it's really easy to do the spectra of this because there are no hyperfine lines. They're all A1Gs. Nothing there, spin 0, right? Can't do anything. It can't identify where it is. You see? It's kind of like those houses in Levittown, Pennsylvania. After World War II, they really had a problem with housing. So the government said, we've got to do something. So they built a town with lots of houses, all from the same blueprint. And they're still there. They were well made. Levittown, Pennsylvania is still there. People don't want to live in it because it's so, you know, I guess, inhuman to not have a different house than your neighbors, right? Well, when you're talking about spin 0 carbon 12, how do you tell which is your house? No way. You cannot tell where your house is. You leave in the morning, you come back, you're going to probably pick another house. There's no way. They're all the same. And, you know, if there'd been a spin on it, you could set that spin, right, in a particular direction, and then you go away and you hope the magnetic field and everything keeps it there, right? You come back, oh, there's my house. There's a spin pointing at the North Star. So that's my house. I identify it, right? And once you identify one house, you identify all the others just by, you know, a road map. So that's the magic of the Bose symmetry. Now, put a spin and a half in there, now you're talking Fermi, and you got a lot more structure you can play with. And just think what the periodic chart would be in Bose symmetry. We wouldn't be talking about it because we wouldn't be here. The periodic chart, if there was a wall, had one element on it, right? There's one element, H, right? And there's big H and there's little h, but that's about all you could get, right? All the electrons just fall right away to one state. There's some science fiction book for you to write. What it was like to live in Achium. Okay. We'll meet again on Thursday, and then we'll meet...
Thursday?
Wednesday.
I'm sorry, Wednesday, and then we'll meet at the exam time.
What day is that one?
I believe it is
I don't
a
know.
Wednesday, but I'm not sure.
Oh. I think
Do you know what it is?
I have a pretty